In this lecture, we will talk about vertex normals and light sources. Shading is the computation of reflected light at every point. To compute the shading values, we need to know the normal vector n, the material properties, and the light vector L. The cosine terms in lighting calculations, as described in the previous lecture, can be computed using the dot product. Using unit length vectors simplifies the calculation. GLSL has a built-in normalization function that can be used to convert the vectors to unit vectors. There is also the concept of front and back faces in computer graphics. So when we define a polygon, it has a front face and a back face. For many objects, we never see the back face, so we don't care how or if it is rendered. Such as spheres, the back faces are not visible because they are enclosed, and in a fully enclosed cube, we do not see the back faces at all. But let's say if one of the faces of the cube is missing, we would be able to see the back face of this polygon on the other side. And now we need to decide whether or not this should be visible. The front and back faces of a polygon are defined by the direction of the normal vector. And the direction of the normal vector is decided by the right-hand rule. So if we have a point here, a point here, and a point here, and if we describe these points in this order, using our right hand, if we curl our fingers around this, our thumb will point in the normal direction upwards. So this would be called the front face of this polygon. And the other side would be called the back face. And we'll set a parameter as to specify whether the back faces of this polygon should be visible or not. Now here we are studying how to calculate the vertex normals. The polygon normals are the normals of the planes that pass through these polygons. So that is simple, and that we have already studied in the previous lecture. Consider these 5 polygons which are adjacent to this point P. We can compute the normals of each polygon individually, that we have already studied. Now we can now average all these normals to come up with a single normal, and that would be the normal of the point P, shown here with n. This is the sum of all these normals. And to ensure that the normal is still a unit vector, we divide it by the magnitude of the resulting n vector. Or we could use the normalize function that is built into GLSL. Light sources are geometric objects whose positions or directions are affected by the model view matrix. Depending on where we place the position and the direction setting function, we can move the light sources with the objects. So we can move them both together, or we can fix the objects and move only the light sources. Or we could fix the light sources and move the objects, or we can move both of them independently. In interactive graphics, users should be able to do all of the above. Now specifying a point light source, for each light source we can set the RGBA values that would define what color and intensity the light source has. And we can set up the diffuse component of the light source, the specular component of the light source, and how much it contributes to the ambient light in the environment. And we can define all these as vector 4s, giving them appropriate names that would be meaningful to us. Position would of course be defined by the XYZ values, and the perspective division W. The diffuse, ambient, and specular components of the light source would be defined by the RGB values. This is red component, this is green component, and this is blue component. So this light has been set as red because you've given 1 to the red component and 0 everywhere else. If we want a white light source, we should give 1, 1, 1 to the RGB values. The last component is for opacity or alpha. The light source color is specified in RGBA. The light source position is given in homogeneous coordinates, and if W is equal to 1, This means that this is a finite location of the light source, because w is equal to 1 is used for points. If w is equal to 0, we are specifying a parallel source with a given direction vector, and it does not have a finite location. Recall from lecture 15, we can have a distant attenuation coefficient, which means that as we move further away from the light, the intensity of the light should decrease. The distance attenuation coefficient is usually inversely proportional to the square of the distance d, where we use this quadratic term 1 divided by a plus bd plus cd square, and a, b, c are user-defined constants. So this ensures that the drop in the light intensity is not dramatic if we set appropriate values for these a, b, c coefficients. Spotlights are derived from point sources. Each spotlight thus has a distance and a color. In addition, it has a direction, a cutoff angle theta. So notice here that beyond theta, there will be no spotlight, and it also has an attenuation function usually defined by cos phi raised to the power e, where phi varies from 0 to theta. All points that are within this cone would be illuminated, and all points that are outside this cone, such as P2, they will have no intensity. And of course, if we set theta is equal to 180 degrees, then this spotlight just becomes a point light source. Larger values of E will cause faster attenuation. As we can see here, if we set E is equal to 1, we get slow attenuation, and this dome is the intensity curve drops slowly. But if we increase the value of E from 1, the drop in intensity is dramatic, it's fast. But in either case, it doesn't go beyond plus minus theta. So that's the cutoff region, and this is how the light source sort of becomes a spotlight.